Alright, it's time for us to cover a incredibly important exercise in analysis. So, let's see here. So this is Spivak, and if you go through this textbook or whatever course you're taking that's using this textbook, and you're not emotionally scarred and you continue to study math, then you'll probably go through Walter Rudin's Principles of Mathematical Analysis next, or some other similar real analysis course, and you'll learn about analytic functions. And this function is really at the core of it's like the core examples of functions which are not analytic. And you'll go through and you'll discuss why are analytic functions important and what are their properties. But anyway, so let's look at this example. So we have this function. It's e to the minus x to the power of minus 2 at points which are not 0, and then it's 0 at 0. So we want to show that f is a C infinity function, meaning that if you take any number of derivatives here, so we want to prove that the nth derivative of f at x exists for all integers n greater than 0 and all real numbers x. So how are we going to do this? We will first prove the claim for x non-zero by induction on n. So we're going to prove that f is oh wait, no, it's not enough to prove that f to the n of x exists. It's f to the n is continuous at the point x for all n greater than or equal to 0 and x and r. That's a really large, really important distinction to make. So we want to prove that the nth derivative of f is continuous at the point x, and it doesn't matter what x or n you use. Okay. So, let's see here. So, let x be non-zero. I claim that, let's see here. I claim that that the nth derivative of n is of the form. See here, what's the form? So it's e to the minus x to the minus 2 times Pn of x, where Pn is a polynomial. And of course it's of this form. This is for x non-zero. Okay, so let's prove this. For n equals 0, so this is the base case. Simply let Pn of x be the polynomial, which is identically 1. Then, because f of x is e to the minus x to the minus 2, for x not equal to 0, then then the function f is of this form already. So that takes care of the base case. Next, suppose n is greater than or equal to 0, and f to the n of x is equal to e to the minus x to the minus 2 times Pn of x for x not equal to 0. Okay? So then what? then if we take the n plus first derivative of f, and we evaluate at x, which is not 0 again. So this is going to be the derivative with respect to x of e to the minus x to the minus 2 times Pn of x. Okay, so if we want to evaluate this derivative, we need to use the chain rule. So first we'll take e to the minus x to the minus 2 and multiply by Pn prime of x. So this is the derivative of Pn with respect to x. Plus, and now my power just went off. That's not fun. Oh well. Well, my recorder and my laptop are battery powered, so that's good for you watching. Anyways, so, this derivative plus, what are we going to do now? We are going to take, we have to take the derivative of e to the minus x to the minus 2. So what's going to happen? If you take the derivative of e to the something, it doesn't change, so we keep that. And then by the chain rule, we need to take the derivative of that exponent. And when we take the derivative of that exponent, the minus 2 will come down, and we'll get negative minus 2, so that's positive 2. So 2x to the power of minus 3. And then we keep the Pn of x here. Okay, so now we can factor out an e to the minus x minus 2 times Pn prime of x plus 2x to the minus 3 Pn of x. And I probably should clarify that when I say Pn is a polynomial, I should say, let's see here. What do you call that? What do you call polynomials with fraction? Is a rational polynomial. Man, I'm really blanking on whatever word this is. It's It's some polynomial where you can have powers of x to negative powers. So it's not just like polynomials when you typically think of them. You have x to the z. You have a constant term, and then you have an x term, then you have an x squared term, and an x cubed term, and an x to the fourth term, and so on and so forth. But you can also have polynomials where you have an x to the minus 1 term, an x to the minus 2 term, an x to the minus 3 term, and so on and so forth. And because we're considering the case where x is non-zero, we don't need to worry about, like, if you have x to the minus 3 or x to a negative power, then you have to worry about, you can't plug in 0, because if you plug in 0, you're dividing by 0. But here you don't need to worry about that because we're not considering x equals 0. So this is a really dumb mistake that I'm making right now, not remembering what these things are called if you have a polynomial that also has negative coefficients. But that's what I mean. So I'll just call it a rational polynomial. I think that's not the right term, but it's the best I can do. Anyways, so we have e to the minus x to the minus 2. So there. If we let, we'll take Pn plus 1 of x, and we'll define this to be the derivative of Pnx plus 2x to the minus third, Pn of x, then Pn plus 1 is a rational polynomial. And I think there's something else here that I'm forgetting about. Because if you take... No, this is fine. This is fine. Okay, cool. Yeah, so Pn plus 1 is a rational polynomial. Because if you take the derivative of a rational polynomial, you're going to get a rational polynomial. And so Pn prime is a rational polynomial. then 2x to the minus 3, that's a rational polynomial, and you're multiplying it by Pnx, which is a rational polynomial. Multiplying two rational polynomials will give you a rational polynomial, and adding two rational polynomials will give you rational polynomials. So Pn plus 1 is a rational polynomial, and f to the n plus 1 of x is Pn plus 1 of x times e to the minus x to the minus 2. And that's what we wanted to prove. So this completes the induction step. Thus, each f to the n is of the form, it's of the form e to the minus x to the minus 2 times Pnx, again for, well, is of this form, and this is a product of two continuous functions for x not equal to 0, and so it's continuous. So thus each f to the n is of this form, and hence each f to the n is continuous at x not equal to 0. Alright, so that's most of the problem. Now the only other thing that we need to worry about is what happens at 0. Now we want to prove here that the nth derivative of f at 0 equals 0. So if the nth derivative exists at 0 and equals 0, then that will finish the exercise. Because what we want to do is we want to prove that each f to the n is continuous everywhere. So if we prove that f to the n has a particular value at 0, then that means it exists there. Am I forgetting anything about let me okay, let's do this. I think I might be there's a slight chance I'm forgetting something about continuity at 0. But I'll deal with that when I get to it. Okay, so let's move on. To determine the nth derivative of f at 0, we use so we know that f to the n x equals u to the minus x to the minus 2 Pn of x for x not equal to 0. So we can use that to our advantage when evaluating this. So we have f to the n of 0. Well, let's do f to the n plus 1 of 0. Wait, where do we, for all I? So clearly f, okay, so here's how we're going to do this. Clearly f to the 0 of 0 is just f of 0, which we know is 0. For n greater than or equal to 0, if you take the n plus first derivative of 0, then you're going to be taking the limit as h goes to 0 of f to the n of h minus f to the n of 0. Oh, we are going to have to use we're going to have to use induction here. So assuming for induction that f to the n of 0 equals 0 for some n greater than or equal to 0, we have f to the n plus 1 of 0 equals the limit as h goes to 0 of, let's see here, what are we taking the limit of? We're taking the limit of f to the n of h minus f to the n of 0 over h. And so this becomes the limit as h goes to 0. And then on top, the f to the n of h is going to become e to the minus h to the minus, e to the minus h to the minus 2. And we multiply by Pn of h. And the minus f to the n of 0, that becomes 0 because of the induction hypothesis. And we're still dividing by h here, so that's good. What else do we have? Okay, so now what we do is we're going to want to use L'Hopital. And so we put the h to the we put all the rational polynomial stuff on the top. And we put the exponential thing on the bottom, e to the h to the minus 2. So now we use L'Hopital, and this is going to become, okay, so we have to take the limit as h goes to 0. The thing on top is going to become, we have to use the chain rule. So if we take the derivative of h to the minus 1, we're going to get minus h to the minus 2. We're going to keep the Pnh. Then we're going to add h to the minus 1 times the derivative of Pnh. And then on the bottom, we have to take the derivative of e to the h to the minus 2. So the e to the h to the minus 2 stays there, and then you multiply by the derivative of h to the minus 2, which is minus 2h to the minus 3. And this is going to be equal to, so I should probably go to the next line just in case. The limit as h goes to 0. Now, the stuff on bottom is going to be, so let's bring the e to the h to the minus 2 by itself. So it's going to be 1 over e to the h to the minus 2. And then let's multiply by the other fraction that we have here. So let's see here. We have this polynomial on top divided by minus 2h to the minus 3. So what's going to happen here? We're going to have minus 1 over minus 2. So we're going to have 1/2. So this should go in parentheses. So 1/2 times, so we've got h to the minus 2 on top, h to the minus 3 on bottom, so we'll be left with an h. And then we have a Pn of h. So that's the first term. For the second term, we're going to have minus 1/2, and now we've got minus 1 on top, h to the minus 1 on top, h to the minus 3 on bottom, so we're going to get h squared on top, Pn prime of h. And what's going to happen here? So we're taking h to 0. So on top, the stuff on top is a little weird because you these rational polynomials here, the Pn and the Pn prime. Oh wait, I guess I should have said something to verify that we can use L'Hopital. So let's look back at this. Okay, so going back to the L'Hopital step, e to the h to the minus 2, when h goes to 0, h to the minus 2, that's going to go to 0. You're going to be dividing by something that gets smaller and smaller, so it's going to be getting bigger and bigger. So this is, the bottom's going to go to infinity. And then for the top, if you actually go back to what the PNs look like, if you actually write out the first few pn's, the exponents get smaller and smaller. So like you start with e to the minus x to the minus 2, and then p0 is just constantly 1. Then when you take the first step, you're going to end up with p1 being, I think you just get minus 2x to the power of minus 3. So you already have an exponent of minus 3. And so it turns out that these rational polynomials that we end up are going to have, like, all of the terms of the polynomial are going to have negative coefficients, and then it's going to be larger than, or it's going to be smaller than -1. So like the first one's going to be -3, then the next one you might have a -5 in there or something like that. But whatever they are, they're going to get they're going to be negative numbers. And so what happens is that if you take Pn and you multiply by h to the minus 1, you're still going to have a polynomial, all of whose coefficients are x to a negative power. And so those are going to go, and so if you take h to 0, it's going to go to positive infinity. And so, let's see here, what you have is you have, so because of that, this thing will be of the form infinity over infinity, and therefore L'Hopital applies. Okay, so now looking back at this, so you could have some strange stuff going on here where you have, let's see here, if you have h times Pnh and you have h squared times Pn prime of h, it's not exactly clear what the degrees of the polynomials are going to be, but whatever they are, it looks like they're going to blow up as h goes to 0. However, exponentials blow up much, much faster than polynomials. So this e to the h to the minus 2, that the growth of that going to 0 completely dwarfs the polynomial term going to infinity, and therefore this is equal to 0. So yeah, that's I was a little hand wavy there. What I would really like to do is, what I think would be good to do here is that I'm sort of using calc knowledge here to say that exponentials grow faster than polynomials. And that's probably something that you were just told in calculus without actually proving it, because proving things is hard, and you don't necessarily want to go through all the work of that the first time you see calculus. Now, if you want to do this in what I think would be considered the right way, what you would do is you would do it the way that's done in Baby Rudin, where you have a chapter where you talk about sequences and series, and you actually can use that knowledge to prove rigorously that exponentials grow faster than polynomials, and they shrink faster than polynomials. And basically, if you're comparing a polynomial growth with exponential growth, whatever the exponential growth does will win in the long run. So you learn that, and then you go on and talk about analytic functions, and you go through this exercise, and because you've already proven rigorously that exponentials grow faster than polynomials, you can use that knowledge to make this conclusion here. But here I think we're using things that we haven't quite proven yet, and I don't really see a way to get around doing that. But anyways, so that's that. And let's see here. The fact that the Pn terms have negative so how do I want to phrase this? The fact that the that the terms in Pn have x's with negative exponents. Well, wait. Okay. Sorry, I'm getting ahead of myself and going back to that thing that I mentioned earlier about having to worry about continuity at 0. Let's finish this up first. Okay, so we have this. Thus, f to the... Oh, power's back. Awesome. Thus, f to the n of 0 equals 0 for all n greater than or equal to 0. Okay, so that's done now. Okay, so we know that the all derivatives of f exist at 0. We know that all derivatives of f exist at other points and are continuous there. Now we need to lastly, we must confirm continuity of f to the n at x equals 0. This is straightforward since we know that f to the n of 0 is always going to equal 0, and the limit as x goes to 0 of f to the n of x is going to be the limit as x goes to 0 of, again, this is e to the minus x to the minus 2 times Pn of x. And what's going to happen here? Here we have x to the minus 2 is going to get really, really, really large, and so it's going to be e raised to a very, very, very large negative exponent, which means that this thing is going to go to 0 because negative x to the minus 2 is going to go to negative infinity, and so e to that is going to go to 0. And this Pn of x, well, that's a polynomial, so even if this thing, let's see here, so some of the terms of Pn are going to have negative exponents. Well, all of them are. So those things will blow up when x goes to 0, but not nearly as quickly as the exponential part shrinks. So if you've got exponential shrinkage versus polynomial growth, the exponential shrinkage will win. And so this is equal to 0. Hence, f to the n is, or hence f is C infinity. I.e., for every n greater than or equal to 0, the nth derivative of f is continuous at every point. And we prove that by proving that f is C infinity on all points x not equal to 0. Then we proved that f prime, that the nth derivative of f at 0 is equal to 0. And then we proved that that is equal to the limit as f to the n, as x goes to 0 of the nth derivative of f at x. And so by sort of dealing with the region away from 0 and dealing with the region at 0 separately, we take care of everything. And so we've proven everything that we've needed to prove. So that's the end of the proof. One other interesting thing about this is sort of strange if you think about it, because like when I first had a professor sort of discuss this function, the way he described it was he sort of noted how this doesn't really make a lot of physical sense. Because imagine if you have a function like y equals x squared. Now, if you look at the point 0, when you plug in x equals 0, you get 0. And also the derivative at 0 is 0. So in a physical sense, there has to be some sort of momentum or force that's pushing this function forward. If you think about moving from left to right on the x-axis, there's got to be something that's pushing this function forward. And where is that coming from? Well, that actually comes from the second derivative, because the second derivative of y, or the second derivative of this function x squared, is 2. So the second derivative is positive, and so that sort of provides some force to move the function forward and to get it to start increasing. Whereas if you look at this function f that we're considering here, I think it sort of also looks like this. I'm not exactly sure what the graph looks like. But at the point 0, the function 0, and when you move to the right of x equals 0, the function starts increasing. So you'd think, okay, well, if this were like the trajectory of like a physical particle, then there must be somewhere that this force is coming from that's going to push it forward. But at 0, all derivatives of f are 0. So there's no force pushing it forward. So it's weird that you have this point here at x equals 0 where f evaluates to 0 and all derivatives of f are 0. So there's absolutely no momentum on this particle. It's just staying put. And then as x increases, all of a sudden this thing just starts moving sort of on its own. Which I guess that's one of those things that's sort of fun to think about it, but it doesn't really help you at all in the mathematical sense. If you want to talk about mathematically rigorously, the only thing you can say is, well, in one scenario you have a function which is 0, but it has some derivative which is not 0, and it starts increasing. But here you have a function where you have the function you evaluate at a point at 0, all of its derivatives of the function at that point is 0, but it somehow increases. It's not the 0 function. And that's what analyticity really is. It's about, if you write a function as like a polynomial with infinitely many coefficients, then are you able to write a function as a polynomial with infinitely many coefficients? And here, of course, you can't, because if you have a function which evaluates to 0 here and all of its derivatives are 0 there, you would think, oh, well, that must be the 0 function. Because if it's 0 there and all of its derivatives are 0 there, that's sort of like the only the thing that immediately makes you think of is the 0 function. But no, there's another function that does that, and it's this function here. So yeah, it's definitely something that you want to, first of all, you want to know this proof, and you want to be able to do it, and you want to understand it, because this really gives you a lot of insight into what types of functions are out there, and you also do really want to take time to reflect on this and really understand it, because being familiar with like these different types of functions these are the types of things you want to these are things you want to have in your toolbox as a mathematician. So anyways, I'm going to stop rambling on about this now and just leave it at this.